Hey guys, Dr. Cadell here. This is the thermochemistry experiment. Thermochemistry is the chemistry of energy flow. And energy is a really funny thing. It's really important and it's everywhere, but you can't see it. But we're going to measure it. And the idea in this experiment can be summed up in basically this equation right here. What this says is Q cold equals minus Q hot. What that means is, okay, remember, Q stands for the amount of thermal energy transferred into or out of an object. And so what this says is that when you put something cold and something hot together, always what happens spontaneously is thermal energy flows from the hot object into the cold object. That's what this equation says. Now we can go a little bit farther because we know what Q is. We have an equation for Q. The thermal energy transferred into or out of an object can be calculated using the equation Q equals ms delta T, this part of this equation here. If we know the mass of the object, the specific heat capacity, that's what S is, the specific heat capacity of the object, and delta T is the change in temperature of that object, final minus initial. Now, in this experiment, we're going to use a calorimeter, which I'm going to show you guys in a few minutes. And the calorimeter itself absorbs some energy. So what we do is we take some cold water, put it inside of the calorimeter, take something hot and different things, which I'll talk about in a minute. And when we add the hot thing into the cold water, the temperature of the cold water rises, the temperature of the hot thing cools down. By measuring those temperatures, the initial and the final temperature of the water and the object, knowing the mass, okay, we can use this equation right here. Now, because the calorimeter itself is going to absorb some of that thermal energy, we need to know how much energy is going into the calorimeter itself. To do that, we measure what's called the calorimeter constant. All that is that's just the heat capacity, not specific heat capacity, the heat capacity of the calorimeter. That's the first part of the experiment. And I'll show you, when we get over there, I'll show you how we're going to do that. But basically, we're going to be able to measure C. That's the calorimeter constant. And what that is that's just how much energy it takes to raise the temperature of that whole calorimeter by 1 degree Celsius. Now, the calorimeter is made of metal, there's some styrofoam, plastic, there's going to be a magnetic stir bar in there, all that stuff together. That's the calorimeter, and it has some constant, some heat capacity, which we're going to measure here. And so when we put something hot into that calorimeter that's going to have cold water in there, that energy is going to go into the water. We're going to use our ms delta T for the water that's in the calorimeter, plus some energy is going to go into the calorimeter itself. That's the C delta T part. And so if we add up these two terms right here, we know how much energy went into the water and the calorimeter, which means, guys, we know how much energy came out of the hot object. And that's going to be really useful for us. So this has, three basic parts. In the first part, we're going to measure the calorimeter constant. In the second part, we're going to measure the specific heat capacity of an unknown metal. And it ends up, guys, that if we find the specific heat capacity of a metal, we can estimate or we can calculate its molar mass, which means we can identify the metal. In the third part, we're going to end up measuring the heat of solution of citric acid. We're going to measure the heat of solution of citric acid monohydrate, also the heat of solution of sodium bicarbonate. And once we get those, then we're going to be able to measure the heat of reaction between citric acid monohydrate and sodium bicarbonate. This reaction right here describes the reaction between citric acid and sodium bicarbonate. The reason we have to measure the heat of solution of both of those compounds, the citric acid comes as the monohydrate, but once we put it into water, the waters go away and they're not involved in the reaction. That's why I didn't write the hydrate here. But as soon as we put those compounds into that water, they're going to start dissolving. They have to dissolve before they can react. And it takes some energy to do that. It ends up, actually, for both of these compounds, that process is an endothermic process. So when you put citric acid monohydrate into water, the temperature goes down. When you put sodium bicarbonate into water, the temperature goes down a little bit. So we have to take that energy flow into account to figure out how much energy, the change in energy for this reaction here, which ends up, by the way, also being overall an endothermic process. So this third part of the experiment, guys, has three parts to it. heat of solution of sodium bicarbonate, heat of solution of citric acid monohydrate, and then we're going to mix the two, we're going to react the two compounds together, citric acid with sodium bicarbonate, and measure that change in enthalpy. That's the idea behind this experiment. Now there's a separate video that I have that explains the calculations for this by itself. I'll put a link to that in the video. So why don't we go over there and start doing the experiment. All right, guys, so the first part is to measure the calorimeter constant. By the way, this is the calorimeter. Top right here, this is a stirrer. The thermometer goes through this plug right here. This cup inside of here comes out. There's some styrofoam in here. This is a really good insulator, works really well. So what we're going to do is we're going to take some water, heat it up. We're going to know its mass and its initial temperature. And we're going to have some cold water in the calorimeter. We're going to know its mass and initial temperature. And we're going to mix them. And by measuring the final temperature, plus knowing those other numbers, we'll be able to find the calorimeter constant. That's the goal of this first part. So what we do is we're going to take a 125 milliliter Erlenmeyer flask, put about 70 mils of DI in there. The exact volume doesn't really matter, but we need to weigh it. So what we're going to do is we're going to put the Erlenmeyer on the balance, tear out the flask, so it says 0 with the flask on there. Take it off the balance because we never pour anything directly onto a balance. And this has some marks in there. There's a 75, so I'm going to just bring it up to somewhere just beneath the 75, and that'll be good enough. Place it back on the balance. That mass there, it's important to record, that's the mass of the hot water for part A. And what I'm going to do is I'm going to take a piece of aluminum foil and cover this. The reason for the aluminum foil is we're going to heat this water up now. And you know, when you heat up water, it starts to evaporate. We don't want to lose any because we just measured the mass. If we lose water, we have a different mass. I'm going to put that on in a second. Before I do that, though, I'm going to start heating up our metal shot for part B. To do that, I'm going to take my unknown number, take it off, record that in my data table, and the conclusion. I'm going to take a 150 milliliter beaker, put it on the balance, tear the balance. So now it says 0, beaker on there. Carefully pour the metal shot in there. At this point, if you're not careful, some of this metal shot, if you just dump it in there, it'll break the beaker. Put this back on the balance. Record that number. That's the mass of the metal shot for part B. Mass of the hot. I'm going to pour this back into the test tube now. Being careful not to lose any of that metal shot because I just weighed it. I don't know how much it weighs. So what I'm going to do now, guys, is I'm going to put this into the hot water. I have a beaker, a 600 milliliter beaker with some tap water boiling over here. Place this in there. Tighten it down so it's heating up. We need to heat that for at least 10 minutes. So that's why we're doing it now, so it can be heating while we're doing the first part. That's for the second part. Here's my water for part A. Take that, hold it with a clamp. Place the clamp in the water. Like that. So it's heating up. I'm going to take a digital thermometer. Make sure it's reading Celsius. Turn it on. And I just poke it right through that aluminum foil into the water. And I keep an eye on that. Once this temperature reaches 95 Celsius or so, then we're ready, we can use it. While we're waiting for that to heat up, we're going to come back over here to our calorimeter. We're going to take the cup out of the middle. We're going to weigh about 80 mils of deionized water in here. So put this on the balance and tear it. It doesn't have to be exactly 80, but close. Good enough. It says 0 with the cup on there. Take it off. Pour the water into the cup. This is going to be our cold water for part A. Record that number. That's the mass of our cold for part A. Take this out, place it back into the calorimeter. We're going to take a magnetic stir bar, place it inside of here, You guys, that magnetic stir bar, that's part of our calorimeter for the rest of the experiment. It absorbs some thermal energy, so we keep it in. Even if there's one part where we don't use it, it still has to be in there. Place this onto a stir plate, turn it on, get it going. Over here, we have a lab quest with a temperature probe attached to it. The lab quest is attached to the computer, which has Logger Pro running. It already is going. So first thing I'm going to do is I'm going to measure the temperature of the water in the calorimeter. That's the initial temperature of the cold water. And it just reads right out down here in the bottom. Record that in my data table. I can take this out. Now that we have the mass of the cold water and the hot water, we have the initial temperature of the cold water. We need to get the initial temperature of the hot water. To do that, okay, we're going to monitor the water. When it gets up to 95, which it's pretty much out already, we're ready to go. So what we're going to do, guys, is we're going to add the hot water to the cold water in there and monitor the temperature. Before we do that, we have to set up Logger Pro. Just one thing, we have to go into experiment, hit data collection, and then click continuous data collection. Once that's ready to go, we're good to go. So let's check the temperature. All right, so 95 is good enough. So now we're ready to go. Keeping the thermometer in there, we loosen the clamp, the back, because it's not hot back here, it is hot up there. Monitor the temperature. We're going to start Logger Pro now. We're going to press collect. So now it's going. And now we're going to monitor the temperature. Right now, right before I add it, I'm going to remember that temperature. Put this in, stirring. Temperature probe in here. And so what I'm going to do now, guys, is I'm going to let this run. And what's happening is thermal energy is being transferred from the hot water into the cold water and the calorimeter. And the temperature is going up. All I need to see is I need to see that temperature stop rising and either level out or start coming back down again. Once it's done that, which it pretty much did, I have what I need. The only thing I need from here is the highest temperature that the water in here reaches. And I already have it right here. So if we look at that, we can see that it's already leveled off. All right, guys, so now that it's reached its highest temperature, we can stop Logger Pro. I can read from there's a table on the left. I can just scroll through that, find the highest temperature. That's the last number I need. That's the final temperature. And that's the end of the first part, part A. Ready for the second part, the unknown metal. What we're going to do is we're going to dump this water out, dry it out. We don't want any water in there because it absorbs energy. We're going to weigh some more water. Do basically the same thing with the metal. All right, guys, so now on to the second part, part B, the specific heat capacity of the unknown metal. So I've already weighed out my cold water, have it stirring in the cup. Actually, for this part, when we put the metal in, the magnetic stir bar won't stir, so we don't really have to stir it. I'm going to, now what I need is I have the mass of the metal, I have the mass of the water. I need the initial temperature of the metal, the initial temperature of the water. I'm going to get the metal now. So it doesn't work very well, guys, to put the thermometer directly into the metal. You don't get a good reading. There's not enough contact, not enough surface area. So what we do, this has been in there a good 10, 15 minutes. So we measure the temperature of the boiling water. It should be pretty close to 100, but probably not exactly. That is going to be the initial temperature of the hot metal, the temperature of the water. They've been in contact long enough to where we can, it's a really good assumption that they're the same. Record that temperature in your data table. Record the initial temperature of the water in here. We can just read it off the bottom of Logger Pro. Now we're ready to go. So what we do is we first start Logger Pro. Take the metal. Dump it all into the calorimeter, put the top on. So this part, guys, we have to agitate ourselves because the magnetic stir bar won't stir with that metal in there. So we're agitating this, monitoring the temperature. what will happen is, and it's already pretty much happened, the temperature will reach a maximum and then it'll start leveling out. And I can tell because I'm looking at the graph on Logger Pro. Once it starts leveling out, I know that I've reached our highest temperature, and we can stop Logger Pro, record the highest temperature that's reached on there, and that's all there is to part B. All right, guys, so now we're going to start part C. In the first part of part C, we're going to measure the heat of solution, the change in enthalpy when we dissolve citric acid monohydrate in water. Then we're going to do the same thing for sodium bicarbonate, and then we're going to measure the change in enthalpy when we react the two compounds, citric acid and sodium bicarbonate. So citric acid first. We're going to take some citric acid monohydrate and weigh out about 1.5 grams. So we'll put an empty weigh bud on the balance, tear it out. Because we never add anything directly to the balance, we take it out. And I see 1.5 grams. Let's see how much that is. All right, so pretty close. Write that in our data table. That's the mass of the citric acid monohydrate. Already measured the mass of the cold water, about 80 mils in the calorimeter. Measure the temperature, the initial temperature of the water. Just read it off of Logger Pro right there on the computer. Once I do that, I start Logger Pro first. And then what I'm going to do is I have the magnetic stir bar going inside of there. I'm going to take the citric acid monohydrate, dump it in, put this on, and watch the temperature. So now the temperature should go down because this is an endothermic process. Once it reaches its minimum, I can stop. One thing that we want to do is make sure that it all dissolves, so I'm kind of moving this around on the magnetic stir plate as it's dissolving. And once it's reached its minimum and then leveled off, we can stop. So it's good to go right now. So we can stop Logger Pro. And we're ready for the next part of part C, which is doing the same thing for sodium bicarbonate. I've weighed out about 1 gram of citric acid monohydrate, about 1.5 grams of sodium bicarbonate. I have about 80 mils of water in there. I measured its mass, so I'm going to now record the initial temperature of the water just by reading it off of the computer screen. Got that, record that in the data table. So now what I want to do, guys, is for the reaction to happen, the compounds have to dissolve and then react with each other. So I want to add them at the same time. So I'm going to mix them together, add one together. They're not reacting yet, they need the water to react. So now I'm going to start Logger Pro. Get this guy ready. Dump this in. You can hear that fizzing, that's because carbon dioxide is given off. Now the temperature is going down. I'm going to keep this reacting until it's reached a minimum and then started coming back up. Once that happens, stop that, record the lowest temperature reached, and we're finished. And that's all there is to this experiment.